Good afternoon. My name is Federico Fierli. I'm an officer in EUMETSAT, and I would welcome you this afternoon to the first one of the short courses. The short courses are a series that we have organized here in EUMETSAT together with experts Europe-wide. And we would like to welcome to that series, and today we do the first one that will focus on the altimetry data sets, and it will be given in a few minutes by our colleagues and experts, Vinka Osmosbuk from the Copernicus Marine Service and the CLS, and by Oliver Clements from the Plymouth Marine Laboratory. But before giving to them the floor, I just would like to introduce you briefly on what EUMETSAT is. So EUMETSAT is an intergovernmental organization and is open since 1986. Our headquarters are in Darmstadt in Germany, and you see in the top left an image of the place where we work. Our task, I mean, in a nutshell, in a phrase, in just a sentence, is to supply the satellite data sets relevant for weather forecast, ocean monitoring, environment monitoring, and the climate, and that we do this operationally, 24 hours, 365 days a year. Our users are multiple. I mean, mostly the weather services of the member states that sits in our council. It is our priority user, but we have many others worldwide, and the range from service provider to academy to science to implementer of business. Overall, in EUMETSAT, we are more than 600 staff who are coming from all Europe, and you see in the bottom the flags of the countries that support EUMETSAT, with many different competencies, going from flight engineers to business, to accounting, to science, to communication, and to training. Next slide, thank you. Yes, I mean, as we mentioned, EUMETSAT manage a series of satellites that you see here in this picture. I mean, there are a lot of them. We have current programs, and we have the METOP that are the polar European satellites. Is Trident. So there are 3 of them actually working in parallel. There are the METOSAT that is probably well known by most of you. Are the geostationary that provides the imaging of the Earth, that is also crucial for the weather and weather forecast. The JSON, the oceanographic JSON, and the Sentinel-3 that will be the object of today's course. We also have new programs that are starting, soon in terms of the satellite timing. So with the 3rd generation of the Meteosat, with much improved capabilities, the 2nd generation of the polar ones, a bunch of new Sentinel instruments and satellites, so 4, 5, 6 that are in decreasing order due to the launching date, and the new program on monitoring CO2. So basically a wealth of data within the next 15 to 20 years, covering almost many of the basic thematics for the Earth environment. What we also do is to make the data available at the best to the users. For us, users is a wide concept, and of course, every one of you is a user for us. And we gather and try to satisfy the user needs. We grant the data access operationally. We provide help and support. We explore application. We make a communication and outreach, and we do training as the one that we do here. One important point, we also need to thank all the partners with whom we are implementing these courses, and especially the Copernicus program. I mean, I see that a lot of you comes from outside Europe, so I mean, it is probably important to mention that Copernicus is the European Commission program for the Earth environment, and this is a decade-long program that is, I mean, the major cornerstone for Europe. The concept is to provide the data for free and information for free through observation and services, and EUMETSAT is one of the implementer. And for this, we focus on the implementation and the data delivery of the Sentinel satellites. So, having said that, and having mentioned that the Sentinel satellites, I leave the floor to Oliver and to Vinka that will present altimetry data, so the sea height data sets from one of the Sentinel-3. So thank you very much for being here. I see that we are many of us. Just a couple of small rules. So I mean, given that we are almost 150, just keep muted and do not put the video to warrant a proper good network bandwidth. And please contribute to the discussion. Of course, it is difficult to have live questions in audio, but we have a Slido. So go on slido.com, as mentioned here in the slide, in every slide, and make use of the code EUMSC1 to put question. I mean, we want to hear from you. Do not hesitate. Any question is a good question, and we will do as much as we can, our best, to answer to them. So I won't take additional time. Enjoy this, conversation, this course with Oliver and with Vinka and Oliver. Thank you very much, and talk later at the end of the webinar. Bye-bye.
Thank you very much, Federico. So yes, I'd like to echo Federico's comments. Welcome all who joined up for this short course today. Just answering one of the quick questions I've seen in chat. If you could rename your name in Zoom to your full name and the country that you're currently in, that'd be really helpful for our statistics. Cool. So Vinka. Vinka is here today as our specialist expert and has worked with altimetry data for a very long time. Now, to ease into this topic, I think looking at the locations where a lot of people have come from, there's going to be quite a few people from the coast. So I think that it's probably fair to say that the majority of the attendees here recognize that the sea is not a perfectly flat surface. There are sort of hills and valleys and permanent features, such as large-scale Gulf Stream currents, for instance. And we also have sort of temporary features, sort of storms and eddies that will be visible. So Vinka, as an expert in this topic area, what is it? What do we care about when we're thinking about the height of the sea?
Well, welcome to everybody, and I will begin to feel very old with everybody saying that I'm working in altimetry. I've been working in altimetry for a very long time, which is basically true. So surface height is something that is going to provide you with everything's moving in the ocean, and in part also with the gravity of the Earth. Everything is moving. It means things like very short-lived phenomena and features like the eddies. We've got eddies in most currents, and here you're seeing them as 8. Most of the maps you will see in my presentation are in 8, so meaning that the color scale is from lower to the higher. And here left you see the eddies in the Kuroshio as little bumps. The white are very steep hills in the ocean, and the blue ones are troughs in the ocean, little holes in the oceans. So things that you won't see if you were on a boat close to them, because even if I'm saying very steep, it's only 1 meter over something like 200 kilometers. But from space, we can see all these features very properly and with a resolution of about 1 to 2 centimeters. So you are seeing here left the eddies in the Kuroshio currents. You are seeing the main Gulf Stream currents and its meanders and its eddies, something like a steep cliff of about 1 to 2 meters over the overlaying ocean. And from this, you can deduce also the currents are going round the eddies in a clockwise over the warm and higher eddies, anti-clockwise in over the troughs eddies, and the reverse in the southern hemisphere, because here all the plots are for the northern hemisphere, but you'll have the reverse in the southern hemisphere. And this is useful in particular to be able to forecast them. So this is the forecasting of the currents from the Mercator Ocean Center for the day after tomorrow. No, for the day after that. And here it's the current speed, and the altimetry data are an essential input in those forecasts, since it enables to have an overview of all the dynamics of the ocean and be able to know it at a given date, enables to forecast it 15 days later. So those are the most variable features, but you've got also more slowly moving things, like here the El Nino. And again, the maps I'm showing you here are 8. It's not temperature. It's linked to temperature, because when you've got warmer water, it's higher. It's like your classical old-fashioned thermometer with a little tube of liquid. It's higher when it's hotter and lower when it's colder. So you see here the latest big El Nino 5 years ago, with this big over 8 area going close to the South America, and below you had a rather important La Nina, the reverse phenomena, in 2010, with that time warmer water keeping close to Indonesia, with wetness with it, while in South America got lower than usual sea surface height, and thus you can have a view of the phenomena from the time it's leaving the western part of Pacific to the time it's coming close to Americas. And this is about 6 months in advance and can be used in forecasts and viewed as different point of view, such as indicator top right, or longitude time diagram, which are showing you the propagation of the phenomena. What we can see is also the very long-term global variation, which is usually called sea level rise. So with a mean sea level average over the whole ocean, we can see for nearly 30 years now that we've got something like 3.4 millimeter per year rise. 3.4 millimeter per year rise may not seem that high, but in fact it's not the same everywhere. It's coming up to in nearly 1 centimeter per year in some area. You can see left in red, getting slightly lower in very few areas, but overall it's rising because of the same phenomena I've just mentioned, warmer water for about a third of that quantity, and from the melting of glaciers, which are bringing new water in the ocean and making it rise. At some point...
Sorry, Federico, just a quick question. Someone is asking to use a pointer, probably to better show the graph. I think that helps. Thank you. Sorry for interrupting.
Thanks. Okay, so the 3.4 millimeter per year left. This is a global average seasonal variation removed for since 93 and down to 1 month or 2 ago. And this is the trend mapped for every point. You can see the trend at that point. Either in red, it's rising. In blue, it's getting lower. Here, for example. And in gray, it's mostly staying the same. So you can see here, it's rising. It's rising faster, and so you can have some problems. Maybe not being flooded all the time, but having at each storm and each high tide. During a storm, you can have your house flooded, or your fields flooded, or your freshwater stocks flooded, which once a year may be boring, but you can keep on going with that. Several times a year, you may think of relocating somewhere else, long time before being flooded completely permanently. So this is the very most demanding data from altimetry, and this is one of the highest results we have, because it's very useful to know, and it's very impressive to be able to have such results with a satellite which is about 8 to 13 kilometers up from us.
Thank you, Vinke. So that's quite an interesting initial sort of ideas of some of the things that you can understand or look at when using altimetry data, from small scale features in a temporal and spatial sense to very large scale, completely global structures, and also over decadal time series as well. That's really interesting. So we've seen a few of these reasons, these applications. I was wondering if you could give us a little sort of summary of how we actually measure the altimetry from space.
Yeah, sure. So we can try like this young guy. I wouldn't maybe recommend it, but you could go at sea and launch a rope or something in the sea and measure the time it takes to go down. You can also use some sort of a telemeter from a plane, a satellite, or from a ship to know how far the surface is. Use a tide gauge, but every such things, except for the satellite and the plane, will be very local and at a given time. The advantage of satellites is that they're going around the Earth at all time, every time, for several years. So how we can measure sea surface height? Yeah, it's a very simplified version. So here you see, this is the satellite. Don't know if you recognize it. This is the surface of the ocean, and this is geometrical shape, called it the ellipsoid. It's an approximation of the water surface. So if we want to measure the sea surface height, the satellite is sending a radar signal towards the surface and then back. And the time it takes to go back and forth is measured from emit to return. Then we are using a radar signal. The radar signal is an electromagnetic signal, so it's going to light velocity. So knowing the velocity, knowing the time, we can compute the distance. Here, h, which is classically named the range. The range is the distance between the satellite and the surface. Now you could wonder why bother knowing this distance between the satellite and the surface. In fact, an altimetry satellite do not only have this measurement, but also a measurement of altitude with very precise instruments. There are usually 2 to 3 different instruments on board to very precisely measure the altitude. When you've got the altitude, when you've got the distance between the satellite and the surface, you can deduce by subtracting altitude with minus the range, you can define the sea surface height. So this is basically what altimetry is doing. It's a subtraction between the altitude and the range. Now, as most things, it's not that easy. Of course, a number of things happens because we are not in the void. So we've got the atmosphere along all the propagation of the signal. We've got also a sea surface which is not stable all the time. We've got tides, we've got waves, and we also have the atmosphere loading on the surface. And every single one of those are corrections which are applied to the altitude minus range I was talking earlier. Everything is subtracted from the rough sea surface height.
So if I'm correct with this, Binker, these are all things that slow down the signal. Is that correct?
Everything happening in the atmosphere, yes, they're slowing down. Either water in the troposphere, we call the wet tropospheric correction, which is measured by a specific instrument on board called a radiometer. We've got the electrons in the ionosphere, which are slowing down and corrected by using 2 different frequencies. And we've got also the oxygen and dry gases in the atmosphere also slowing down. Now, the things happening at the surface, like this atmospheric pressure or the tides, are either negative or positive, but the convention is that everything is always subtracted. So this is quite simple mathematics, and you can use such data when you're using the level 2 kind of data, which are provided in particular by EUMETSAT. You've got all those corrections, and the main point is that you may not want one of them because typically the tides are not good enough in your area. We are using for correction global model tides, but if you're living and if you're working on say the Great Barrier Reef, the global tide model may not be that good. So you may wish to remove, not use the provided tidal correction, but rather to replace it with a better one fitted for your need in your area. So the level 2 data are the data that enable you to do such things. And there's kind of do-it-yourself data. And you can have data all over the ocean, provided the satellite is going round.
Oh, that's really cool. So from this, what we've just discussed here with the satellite receiving this, sending and then receiving this signal and doing its orbits, does this then give us a complete picture of the altimetry of the oceans?
Complete with all over the place. Here left, you see this little animation, thanks to Australian to have done it in the past. The little orange dot is the satellite, and this black line is its orbit. And below, you see the Earth rotating below. The red lines are the actual measurements you will be having from the satellite. And the blue areas in between those red lines, you won't have data from this particular satellite. So left, you've got the Topex Poseidon or Jason satellites. It's the same orbit, and the next satellite to be launched in 2 months will take over that very same orbit for continuity reason. And for this satellite, you have about 300 kilometers gap in between two of those lines in this mesh of data. Right, you've got Sentinel-3. And for Sentinel-3, you'll have only 100 kilometers in between two tracks because it is going over the same points only every 27 days, while Topex and Jasons are going over the same points every 10 days. It's a compromise. You can't have both. You can't have a fine mesh with a very frequent revisit. You have to choose depending on your needs, or you can do like a Sentinel-3 and A and B, because with Sentinel-3 A and B, you will have only 50 kilometers in between two consecutive tracks using the two satellites. Now the idea is that we are indeed using several satellites, not only Sentinel-3A and Sentinel-3B, but all the satellites that are available at a given time. So here you see the kind of data you will have through the Marine Copernicus service with the intercalibrated in level 3 from all the satellites that were available at that day. So you will see different slope in the tracks, and those are the kind of data you really have with an altimeter. And using interpolation schemes, using data before and after that date, we can fill in and have a gridded data set, which quite large number of you have used, if I read correctly the poll. So this is very much easier to use. However, be aware that you have interpolation in between the tracks, that you have some kind of smoothing, so it might not be the best for your given use, depending what you want to do. In particular, most of the forecasting models prefer to use the along track data than the gridded ones because they want to master this interpolation within their own model rather than use the one we are using to produce the grid. but the grids are very nice and easy to use. And for the beginning of the continuous altimeter era, meaning the early 90s, we've had at least two satellites working at the same time. And these days we've got even more than that, with 7 satellites working these days. And a few new ones, Sentinel-6, I mentioned in 2 months from now, and Chinese satellites and other ones. So we've got a quite dense mesh of tracks these days, and this enables us to have more precise data provided to the users. And thus, you can have confidence when you're using that. I just wanted to be sure that you understand that there are a number of processing behind those, but still we are not inventing the data. You can see here, for example, this red part of the track. You can see it here as an eddy of the one of the Alboran gyres. Or you can see here, maybe, well, it's not the Jupyter gyre, but something close to it, and so on and so forth. So the data are interpolated, but we've got a number of proofs that they are really there.
That's awesome. Okay, so yeah, so we have these individual satellites giving us our along track data, and then we have these level 4 merged data sets, which take data from many different satellites and interpolate them to produce these gridded images. So one is a sort of a one-dimensional array of numbers, and the other one is then a gridded image. So they have very different sort of uses. We'll showcase some of those uses later. I was just wondering, Vinka, if given the experiences you've had with altimetry, if you could maybe show us a couple of interesting use cases where you have actually used altimetry data in other fields.
Yeah, well, I've selected 2 very different examples. One is a turtle in the Mediterranean. Please meet Vita, a loggerhead turtle, which was captured in the Balearic Islands and fitted with an Argos beacon. Then it was tracked for several months, and as all our marine animals, it's living in an environment of currents, temperature, nutriments, and so on. So knowing the sea surface heights and the associated currents can be useful to understand such a turtle way of moving. So you see, this is the dynamic topography, and yep, you see the turtles going round the eddies, and you'll notice it's going faster when it's going around a given eddy. This is not because the turtle is deciding to go faster. It's probably mostly because the currents are faster. Since if you're looking to snapshot here, I've drawn the current speed, and you see the currents here are faster around the eddies in the clockwise here, anti-clockwise there, than, for example, here where you don't have an eddy. So you see the example of a clockwise eddy, a warm eddy, a bump over the ocean, and right you see the counter example, and you see the turtle is going in the right sense around them, because it's going with the currents. We don't think, well, biologists don't think it is aware of going faster. Mostly it is probably going faster because it's swimming with the currents. So, oops. Oh. Got to switch off the pointer to launch the animation, sorry. So just for the fun of it, yep. And well, we lost the signal of the Argos beacon, but this little turtle might still be living very happily in the area. So another example, quite different, is the sea level at Miami. Here you see a picture from plane of Miami, and you see it's very, very low over the sea, about 1 meter, which means that at some points they can get flooded, like left. So for such areas, the question is to measure what can happen to them in order to be able to mitigate the effect, because when you've got floods like this, you may have electric network going off, and metro, if you do have a metro flooded, and so on and so forth. So planning in advance mitigation and trying to avoid as much as possible the consequences is foremost important for the county where Miami is, Miami-Dade County. So with altimetry, we can measure the sea level change in the open ocean, not very, very close to the coast. We can't say that on the island of Miami we can measure it. But with knowing that, what is happening in the open ocean, and with the in situ network we can have, like GPS gauges and the DORIS, which is one of the precise orbit determination instrument on board most of altimetry satellite. It's possible to better know what can happen at a given coastal point. And in particular, the question is what the land is doing, because we know the sea level is rising, but if the land is also rising, it's not so problematic than if it's going down. Here, in fact, we can see that if we make the difference between the tide gauge and altimetry, we've got about a 1.5 millimeter per year difference, and meaning that the land is going down, which is not a good news for Miami inhabitants, with sea rising at about 6.3 millimeter per year in the area. The error on that measurement at the global scale is about 0.6 millimeter per year. So those are the way you can use altimetry in conjunction with other data. For the turtle, you had the Argos tracking system, but you could also compare the track of the turtle with chlorophyll and see if the chlorophyll is accumulating around the eddies, or you can have a look also at the sea surface temperature, because turtles don't like temperature lower than 15 degrees Celsius. And here, with the combination of in-situ measurement and satellite measurement, you can see what's the effect of a global sea level rise can have locally. But stress that for that you really need to know what solid land is doing. Otherwise, you can't really tell what will be happening. And now it's your turn to investigate the data.
We've actually decided to change the process a little bit, because there's been quite a few questions have come up in Slido. So we're actually going to do a short Q&A session now, as well as at the end.
I thought so, but I need to conclude something.
So I think Rosa, if you'd like to take over the screen. So we've had I think 14 questions come in, and we'll do our best to answer. We'll do our best to answer as many of these as we can now. Any questions that aren't answered during this phase or in the Q&A session at the end, we will make sure that if the question is associated with the name, we'll get an answer sort of to you at some point. So on our first one, any follow-up activities to this lecture? On this specific course, no. However, there are future courses, and I will show you where you can go to apply for those towards the end of the course. And then that will give you access to larger training events. So we run weeks-long training events as well. And we do have one of those coming up soon, which is still open for registration for 2 days. But again, I'll explain more about that later. On to a sciencey question. Can you explain how do you do the interpolation? I'm assuming it's just applying a standard interpolation directly to the data.
It's more complicated than that. I can give you the references because I can't in a few words. It's more complicated than a standard interpolation directly to the data. It's not only a kind of smoothing. It's taking into account a number of things happening before, after, and things we know about the dynamic of the ocean too. I can give the reference.
Okay, thank you.
An article.
Yes, we'll add that to the information that gets sent out to all the attendees, which will include links to the presentation and the recordings as well. The next question: how many core that satellite could avoided? Is there any effect for blind zone in the ocean? So I'm assuming this is to do with the sort of the grid that the Sentinels produce as they're making their along tracks. And I would suggest, I mean, Vinka will answer properly, but I'd assume that the interpolated level 4 data sets are our attempt to fill in those gaps.
Yeah, definitely. The correction, that if you don't want to bother with the correction, I would recommend you use also the level 4, the grids data, because everything is applied there. But they can't be avoided at some points in the processing. Except if you want to work on tides, you will avoid correct from the tides, and then you will study the tides with the altimetry measurements. But otherwise, all those corrections absolutely need to be applied, but they are already applied in the level 3 and level 4 data. So if you don't want to bother with knowing which one you need to apply, you can. This course was to explain you what's behind the scene so that you can use those data, completely understanding what you're doing when doing so.
And then the next question is a bit similar, but this is then obviously down to regional differences. You touched on this a little bit with the maybe applying a different tide model to the interpolation. This question is asking whether we use any different datums depending on the area because of the geoid of the Earth not being flat.
Well, the datum used is basically we are using an ellipsoid, which is not exactly the same everywhere, but which is mathematically possible to retrieve. Then if you want to work with dynamic topography, you will be removing the geoid height, so the gravity field effect on the water surface. This is something that is coming from mostly the gravity missions that ESA or NASA launched, like GOES or GOCE, if you're Italian, mission that enable to have a much more precise geoid so that you can retrieve it and use the sea surface height with respect to the geoid. Then you can also work with only height, meaning the anomalies. You will find it named as sea level anomalies or sea surface height anomalies. And those are available through so level 2, level 3, and level 4 data if you want. And then you will be working with the difference between the sea surface height at a given date and the average of it over a long period. So you can use those datum, but you will never use the depths because we don't know well enough it, and because it's not, it wouldn't be practical to work with this depths.
Mm-hmm.
Because what we are looking for is what is happening on the water column,
Mm-hmm.
not its depth.
Okay, that's interesting. So the next question is one that, oh, it's just been taken over by another one. I'm going to go, I'm going to go to the coastal areas one, just because I actually have a specializing in ocean color, and coastal data is always a bit of an issue with ocean color satellites. I'm just wondering with this question, which thing there, it says, how can we measure the sea surface height near coastal areas since the wave propagation is affected by the change of the mean water and land, and how can we correct the data for this? Is this a topic that's sort of an area of study in altimetry, as same as it is in ocean color?
Well, the coastal sea surface height near coast are something really tricky. Not because of waves, because in fact we are measuring a large enough area to average the waves, except for little effects that I mentioned as sea state bias. But mostly we are looking at ground print, which is about several kilometers wide. So in fact, the waves are average. We can retrieve the waves from the from an altimeter, but looking at the way the radar signal is going back, because it will be more flat when you've got waves than when you don't. So waves is not the problem with coast. It's mostly that when you've got a mix of land and water under the footprint of the satellite, it's really complicated. So there are a number of projects trying to improve that. There's 3 to 4 projects ongoing to try and produce really good coastal altimetry data. But those will always be a long track ones. There's no point in trying to do them gridded, but they are not in the standard processing for now.
Okay, thank you for that. That's interesting. The next question we have on here that is visible, do you have any suggestions for resources we should access for further reading? I think any resources that we know of, we'll make sure that there are links added to the Moodle afterwards. And then also I would recommend then, as a further learning option, some of the other courses, but again, I'll highlight those towards the end of the session. We then have a question from Louis Valencia. Is there any altimeter product that only retain the tides?
No. We
we
have we have one field in the level 3 or level 2 data with representing the tides. But if you want only the tides, you'll have to go to the tidal model. Aviso is distributed in one, but it's a tidal models that is used to correct the data. It's not measured.
Yeah, and most of those tidal models are built around there is a huge international network of tide gauges that feed very precise measurements into those models to continually improve the modeling of the tides.
Yeah, and they have been improved by altimetry in the open ocean too.
Okay. The next question is maybe a tiny bit off topic for the EUMETSAT Copernicus marine that we're talking about. However, I could maybe Copernicus does have a land surface, and they are dealing with inland water. I'm unsure if they're doing altimetry as part of the inland Copernicus.
Yeah.
They are? There we
Yeah,
go.
there. You've got the lakes, I think, in EUMETSAT data. Or if you're interested in rivers and lake, you have to go to ESA for the level 2 data or to the Land Copernicus Global Service.
Yeah, and I'd always recommend going to the Copernicus services. They provide excellent sort of data.
Yeah. We are the one providing them.
Well, yeah, exactly. It's excellent data.
I know.
We then have a question that is specific again to some of the data we've shown in the presentation. So on the first curve, this is on the sea level rise chart. It looks like the data since 2011 is actually exponential and not linear. Would you care to comment on that, or obviously
we're very much afraid it is the case?
Yeah, interpreting that data is quite a few people's careers. So
yeah. It looks like yes. In fact, we are a bit cautious about it because on the very beginning of the curves, we have still some correction to do with the very first year of the TOPEX Poseidon satellite. So we are a bit cautious about showing it, but the latest results have shown for maybe 2-3 years that yes, it seems to be accelerating. Exponential, I don't know, but accelerating and not linear, yeah.
That's a good answer, but a slightly depressing one.
I'm afraid so.
Yeah. Okay, thank you for that. We then have another question to do with SWAP missions. We know there are many studies already confirming the feasibility of SWAP mission. Would you have any comments on that?
Launch in 1 year and a half.
It will come, is the short answer.
Yeah, it's very much ongoing. The satellite is being built, instruments are included on the platform, and the simulated data are very encouraging.
Excellent.
Next, we will have to see with the real thing.
Okay. We've kind of answered the next one of increasing sea heights, the same area of our current. The next question, which is a very nice and easy one, do the altimetry data are freely available and how to acquire download? Yes, they are freely available. And I will be showing you when we finish this Q&A section where you can go to get those data, both the level 2 and the level 4 data, and they are both freely available. The next question, any interpolation data gridding is available? Yep, those would be the level 4 products. Those are made available via the Copernicus Marine Service, and we'll highlight those shortly. So that nice easy one. The next one, which instrument is used for measuring altitude parameter? That would be the SRAL instrument, I believe. Or is that Doris that's part of it?
You've got a laser. Which, well, we call it an instrument, but it's basically a mirror with a station on Earth sending a laser beam towards the satellite. We've got GPS, and we've got the Doris system, which is a French system working with Doppler shift, with about 50 stations all over the Earth. And combining all this, including in real time, especially for Doris, we can have the altitude within 1 to 2 centimeters.
Excellent. Well, that's good. I'm actually going to jump because I can see the full list of questions, and I see there's a few of them to do with the observed accuracy for things like mean sea level and the observed accuracy for the altimetry. I was wondering if you could give us a brief overview, Vinka, of the levels of accuracy that we can expect from these sorts of sensors.
Well, it depends if you're looking at instantaneous measurement or a bit average. The accuracy of the mean sea level is obtained through the averaging of the global sea surface height. So it's very different from the one you can have instantaneously. Instantaneously, it's about 1 to 2 centimeters. It's less accurate when you've got waves, high waves.
Mm-hmm.
But it's something like 1 to 2 centimeters. It's an ongoing project to add really at each and every point an accuracy. It's not yet the case. Should be soon, but it's not yet the case.
Excellent. Okay, so we'll just end this part of the Q&A now. We will do a Q&A at the end of the session as well. But like I said, any questions that we don't get to during the event of the short course, we will we'll endeavor to make sure you get an answer.
Okay, thank you, Ollie. So now it's your turn on the demonstration of the data, of the Copernicus data. While you prepare, just the answer to the question that we had about the availability of the material. Yes, this will be made available through the Moodle site where you have enrolled to the course. But we'll provide again the link at the end of the course in order that you can gather the slides, PowerPoint, and a recording of the session. Thank you, and please go ahead, Ollie.
Excellent. Okay, let me just pop up my screen. Okay, so this is going to be a quick session now where we highlight the places that you can go to get altimetry data. We've already discussed that there are two different sort of levels. We have the along track level 2 data and the gridded level 4 imagery data. So first off, what I'm going to do is look at where you can get some of the level 2 data. Now, the easiest place and the best place to get the last year's worth of data is from a website called CODA, which is provided by EUMETSAT and Copernicus. And this has all of the Sentinel-3 data inside for the previous rolling year. If you need data that goes back further than that 1 year, you can then also go to the EUMETSAT data archive, where they then have their full data sets. But when you do come to CODA, I'm already logged in, so it hasn't asked me to log in. But the first time you come here, if you aren't already logged in, it will redirect you to a login screen. And then once you've logged in or registered an account, which is free, it will then bring you back to this search interface. So this search interface has a sort of a classical slippy map. So you can drag and zoom in with your mouse. So I can click and drag, and I can use my scroll wheel to zoom in and out. For searching, you have a search box here, which actually does have quite a few different criteria we can search in. But the first thing we'll want to do is actually give a search area. This is just a sensible thing whenever you're searching for data in some of these tools, is to limit the results based on only the area you're interested in. So to do that, we come down here to the bottom, and we have a box here called box or polygon, and we'll just select polygon. And then we can just click on the map anywhere we like, click 1, 2, 3, and then double click to finish. So do that again, 1, 2, 3, 4, and then double click to finish. And so that then gives us a polygon. What we then need to do here is select how we'd like the data to be displayed to us. So we're just going to sort it by the ingestion date. And we then need to choose the start and end dates for where we would like to look for data. So if we just take the start of September, and then we need to choose the fact that we're using Sentinel-3. And we are going to be using level 2 SRAL data, which under the product type of the Sentinel format, there is a specific data format for Sentinel-3 files called SAFE. And the naming of that is a convention. And so this is part of that naming convention. And it just got rid of it. And we don't actually then need to click anything short time or non-time critical. But for the purposes of this search, when we don't mind, we'll look for any. And so we can then just click search. And this is now searching the available catalog of data, and we'll eventually come back with some lines. Now, this is highlighting what, sorry, just putting in chat window, I've got Zoom in the way. This is highlighting what Vinko was explaining, where the level 2 data are only the lines underneath the satellite. And so you can see the gaps in between each of the lines here. And each data set that was available through this Coda online platform is one of these level 2 data sets. These are then all of the ones that matched our search criteria. And you may notice as I hover over each of these, one of the lines on the map gets slightly thicker. So it just highlights which one you're looking at. There is another way to do that. If you come down to the map here and you click pan, so this gets you away from the polygon drawing and just takes you back to the ability to move the map. You can actually then click on an individual line, and again, it will highlight it, and it will also highlight it in the list here. So if you click on another one, you can see it's now highlighting this one down here. You have the ability to do a quick look, which for a SRAL data set doesn't provide you a huge amount of interest because, again, this isn't imagery data. So there's no image to quick look at. Why would you want to do this then? Well, the reason would be just to have a look at the full footprint to see where the full half orbit is going. That may be useful for you if you're interested to see where that is. Each of the data sets that are available in this Sentinel-3 safe format, this is what you're seeing here. For the SRAL data, has 3 different data sets inside it. The standard measurements, reduced measurements, and enhanced measurements. These may be downloaded individually using this blue button here, or you can download all 3 of them with a manifest file by just pressing the little arrow with a flat line button down here. And if we press that, it will then ask us to download a zip folder. And you can see it's not particularly large, and so we can just save that. And so we've now got a zip folder which has a safe format netcdf in it. I'll show you using that data in a second. Okay, sorry, I'm getting distracted by chat. I'm just going to close that. Okay, so that was Coda. So it's very simple. You draw the area you're interested in. You fill in the criteria that you're interested in here, which will primarily be the sensing date. I personally always search using the sensing date because that's normally the one that's most important. I'm interested in the phenomena underneath the satellite at a given time, whereas the ingestion period is when that data finally makes it from the satellite to the ground station and then to EUMETSAT. So that may be less important it is certainly to me whenever I'm searching data, because the sensing period is what's often what you're most interested in. So this was Coda, and this is how you get access to the level 2 data. Now, the level 4 data that Vinka mentioned, these are the images of altimetry data that are produced by the interpolated data from multiple satellites. Those products are made available by this group called the Copernicus Marine Service. It used to have the full name of Marine Environment Monitoring Service. And this is the website up here. And to get to data, once you're on here, you'll go to this one here, the services portfolio, which will then take you to their data search. And then here, to download data, you will need to sign in. So we can just do that here, quickly log in. And it will bring you back to the search. So the search for this one isn't quite as interactive as Coda, but it does provide access to a lot more data sets. So what you can do is you can search by regional domain. Now, these are the majority of the domains that have been created under the Copernicus program for this environmental monitoring service. There is obviously a heavy focus on European data for these subsets. However, they do produce global ocean data sets, which obviously will then cover the areas you're interested in if they're not covered by these smaller areas. You then have a parameter search. So for the purposes of this search, we're just going to look for sea surface height. But as you can see in here, these are the set of key parameters that have been decided by the Copernicus Marine Environment and by a large group of scientists as to the most used and the most valuable data sets that can be made available to the community. Again, we will just search for sea surface height. So that's actually then reduced the number of products that we're seeing here to only the ones that match these criteria. So we only have data which currently covers the European Northwest Shelf, which selfishly I am based around here. And so these are the data sets I will tend to look at the most. And you can actually sort of infer a little bit about the data here. So you can see that this is a full model data set, a model data set, a model data set. This is an observations data set based on level 2. And then this is a gridded observation for level 4. So this is the sort of the data that we'd be interested in looking at for if you're looking at a global event. And so to download some of this data, first we'll just click on it here. And that then loads us up the document, the data description sheet for that data set. You'll find here quite a lot of information, both about the specifics of the sensing that are involved, the sensors that are included in this data. So as you can see here, it says it processes data from altimeter missions included on, if I make that bigger, JSON 3, Sentinel 3A, Higher 2A, SRAL, Attica, Cryosat 2, JSON 2, JSON 1. There's a lot of satellites, and those data are all interpolated and combined together to make these level 4 data sets. So you've got information here about the actual data, how it's collected, how it's produced and processed. We then have an information about the geographic coverage. Now, obviously, it's a global data set, so this one covers the whole globe. It gives you an idea about how the data are produced. So this is a satellite observation level 4 data set. It tells you the data variables that are available in here. So we have sea surface height above geoid and sea surface height above sea level. It gives us our spatial resolution, the coordinate reference system for the data, and the temporal resolution. So that gives us all of the metadata. So how do we actually get the data? We go to this download product button here. And then we can choose the data set that we're looking for. So let's just say we're looking for monthly means. And I need to change the size of this because it breaks the form. And in here, you see, we can now add in I'll change that to -90. There we go. We can just type in our coordinates here, and it will then subset the data. So if we're interested in looking at the El Nino event, maybe we could take a subset like this, which just shows the Eastern Pacific. Once you've got the area that you're happy with by just changing these numbers, like I say, this will change and update to show you the area that you've selected. And if you're not happy with it, you can just reset it and it will reset. I don't know why these are defaulting to silly numbers. I'll raise that with the CMEMS group. We then have, in the same way as we did on the Coda platform, we have the ability to choose the start and end date for the data that we'd like to download. Whereas on Coda, it was just for the data that we were going to search, because you can download only individual files at a time. Whereas CMEMS allows you to download a time series of data all in one go. So if I wanted to say take a month's worth of data for the globe, I could just scroll down here until I get to say, okay, these monthly averages. So let's take a year. So if we go to September 2018, can't find it, there it is. And so this is now going to give us data from 15th of September 2018 to the 15th of September 2019. This data set doesn't have a depth, so we don't need to choose anything there. For some model data are often produced with varying depths. So you have sort of a 4-dimensional data set. We don't have that issue here. And then the variable that we're going to be looking at is the sea level anomaly. And we only have the one variable, so we don't need to change anything here. And then we just hit download. And because I'm already logged in, it's not going to ask me to log in again. It's not going to ask me any information. What it's doing here is it's just calculating the size of data that I've requested. Now, I haven't tested this query before because I was just doing local UK data, but I thought I would do this just to see if it does trip. So it doesn't. So Copernicus has a limit on the individual file sizes you can download. If my data selection here had gone over 1 gigabyte, it would just ask me to reduce one of the parameters. So either reduce the amount of time for data that we were looking at, or the amount of variables that we were looking at. For this data set, that wasn't an issue. It was only 74 megabytes, so we didn't have to do that. There is no limit on the total amount of data you can download. You just have to break it down into these manageable chunks of 1 gigabyte. And as you can see, again, that's then downloaded a .NET CDF file that we can then utilize in Python or other programming languages. Yeah, so that's data access. So we had, I need to move the Zoom thing, it's blocking my way. So we had Coda for looking for level 2 data and then downloading it. And we have the Copernicus Marine Environment Monitoring Service for finding level 4 data and other data sets that we're interested in, and then downloading those. So I think what I'll do now is I'm going to jump straight into what could we actually do with these data in a programming sense. So this is one of the areas where my speciality lies. Is I'm a computer programmer. I've been working in the marine field for a very long time though, so I'm both a marine scientist and a computer programmer, but computer programmer first. And so we'll be showing you how to open a file and quickly render it in Python. That's the programming language I use, and primarily. And for doing this, we'll be using a system called Jupyter. I will also be able to make these notebooks available to you through the Moodle, so you can download these and utilize them on your own or have a look at some code. So the first data we'll look at will be the level 2 data. I was running these earlier, so they're all open. And so we've got the level 2 data we've downloaded from Coda. So we want to have a look at it though. So what we'll do in Python, and I won't spend too much time on the actual sort of the intricacies of the Python, just because this isn't a Python short course, it's an altimetry short course. If you want to learn more about these programming elements with these data, I'll highlight some courses that you could maybe apply to in the future. As a little basic intro, when working with our NetCDF data, XArray and NumPy are two of the most common libraries that you'll be using. XArray has all of the features of the NetCDF core library, but then adds on a few extra bonuses. And NumPy is the sort of the numerical Python library, and it makes working with arrays really, really fast. And a NetCDF file is just an n-dimensional array. And so we can use XArray to open it and NumPy to investigate it. We then have Matplotlib and CartoPy. These are basically plotting libraries in Python. Matplotlib is the core plotting, and then CartoPy allows us to do geospatial plotting. So initially, again, I won't spend too much time on this. All we do here is we just set up some of the basic plotting parameters that we're going to be using for the rest of this notebook. And we just let Matplotlib know that we're in a notebook so that it can pop the outputs in line. For our use of the CartoPy, we just need to tell it what land resolution for our border file that we'd like to use. And that's about all we need to set up there. This is just me telling Python where my data are using an operating system agnostic method. So it doesn't matter if you then if you're running code on Windows or Mac, if you use this method and this way of building your paths, they'll always work. Each operating system has its own intricacies, and this just makes sure that you get around those. So to open the file, we use the XArray open dataset. And this then gives us access to the NetCDF metadata and the actual data. Now, the first thing that we can look at is the variables. And so these are the different variables that are available inside one of the level 2 files from Coda. We won't be going through all of these here. And this is the standard measurements. We could reduce this by, if we comment this one out, in Python, if you put a hash before a line, it comments it out. And this line is now ignored by the Python interpreter. And we can go to reduce measurements. And if we just run this box again, you can see that the number of variables is significantly less. Again, depending on which ones you wanted to work with, as I highlighted in Coda here, if I go to one of these again, you can see that it has these 3 NetCDF files exist within the download. So these 3 NetCDFs you will get by default if you download some data from Coda. So we can then do a little bit of exploring the size and statistics of the file. Again, I won't spend too much time on this, but this is just to highlight that the structure of the data inside a level 2 file is a one-dimensional array. And
Ollie,
Yes.
There's somebody asking if you couldn't enlarge your screen a little bit.
Thank you. Is that better?
For me, it is. I don't know.
I'll just wait for
For
Paolo.
the people who asked.
Okay, yeah, we've had
Yeah,
one yes already. Sorry about that, guys. Okay, yeah, so we're just going to explore some of the statistics. Again, this is just to highlight that these are one-dimensional arrays. So we can take the data from the netcdf file by using the variable object, and then we just pass the name of the variable we're interested in to this variable object, and then we can take a copy of the array. What we can then do is we can then use the NumPy library has this function called shape. The shape of a NumPy array is often important because they can have any number of dimensions. So it's useful to be able to see what the shape of an array is. And what we can see down here is that the array shape is one-dimensional. It's a single array with 2100 items in it, but it is not a two-dimensional image. It is just a one-dimensional array. We'll skip over this. These are some of the things that we cover in our longer courses where we talk about some of the quality flags that are associated with data. We will be skipping over those just for the moment. So just so that we can now look at what one of these half orbit files looks like, we're going to plot our one-dimensional array. And I'll run through this code in a little bit of detail, but we then reuse this same code over and over again for the rest of this notebook. So we're using the matplotlib option here to just create a figure. And because we want this to be a geospatial image, we're going to be using the cartopy functions, which will then allow us to do things like pass in a projection. So this then tells cartopy how we would like our map to be rendered. Here we're just pulling out a few statistics from the file, useful for our coloring. And here is where we're then actually making the data. Now, as you can see, because our data are a single array, what we're actually going to do is treat them as a scatter plot associated with the lat and long as their x and y axis to give them their location. And then the color of them will be the value of the actual data point. And then what we have over here is just some setup for our plot, where we're just going to ask the color scale, the bottom of our color scale to be the lowest point of our data, and the highest point of our data to be the highest point of our color scale. Then we just have, this is boilerplate to set up the map. So we just tell the Python we want coastlines and we want to have the land. So if I scroll down, you can see the black line is our coastlines and the beige land polygons. This is this feature here. And we just want to have some grid lines because it makes the data easier to understand. And we want our text to be of a particular size and color. So that the data are more understandable as well, we'll have a color bar. So whenever you reinterpret numerical data as a color scale, for your users to then be able to understand it, you need to have a color bar, which then allows them to sort of convert back from color to numerical value. And so this is what happens when we pass in one of the Sentinel-2 half orbits, is we have this line like this. Now the value at the data point that we're looking at here is the range. And if you remember that from Vinka's presentation earlier, that is the height above the surface. We now are going to plot a few different variables that are the more science, the variables you'd be interested in. But all of this code is the same. All we're doing is just changing the variable that we're actually plotting on the map. All of the actual plot setup and the map cartopy setup are identical. We just changed the variable that we're taking from the netcdf. So here you can now see significant wave height. If I scroll and make it a tiny bit smaller just so I can scroll and have it all on screen. And so you can see here, significant wave height is measured in meters. And you can see from here, we have clearly there is a storm off the west coast of South America because we have a very high significant wave height here, which is increasing, peaks, and then decreases. So it would seem fair to assume that there's probably a storm of some variety here. And then as we go up through into the northern hemisphere, you can see that actually the Atlantic was very boring when this satellite overwent. Very, very very few waves, only in the region of sort of 1 to 2 meters. And again, we'll plot a different variable now. And this is one of the data sets that's available with the level 2 data, is we also have wind speed available. And it can be interesting to correlate sometimes the significant wave height that you're seeing with this wind speed. And so we can plot that again using the same approach. And this gives us a little bit more information about what we were seeing off this west coast here. So our significant wave height is matched by an increase in wind speed. And this is in meters per second. And we can see here that there is a significant increase in our wind speed, with then a significant decrease as we move away from the storm. Now, interestingly, there are also some pretty significant wind speeds just over around the coast, but those don't tend to correlate with a change in sea surface height. Now that can, significant wave height. Now that can often be because the storm that what you're seeing that's producing the wind is over land. So it's not having a swell effect on the water, it's just having a sort of a wind blown effect on the water. But I like to think that the one thing you take from this is that the level 2 data, they are useful and they provide you a lot of information, a lot of variables. But if you're interested in a large geographic area, then they may not be the best data set for you to have a look at, because it is just this half orbit. So if I was interested in this whole area here, I can infer that maybe the data here are similar to the data here, but I can't know that unless I were to go and look at some sort of level 4 data, which is what we'll look at now. This one down here was just then the sea surface height anomaly, but it's the exact same plot, we just changed the variable. So for level 4 data, this is all bigger again. So for level 4 data, when you take data from CMEMS, as I mentioned, it can come in a time series NetCDF. And so what that means is it's a NetCDF with multiple images in it. And that gives you a lot of power. It gives you the ability to look at a particular area over time for changes that may be seasonal or may be specific to an event that was happening. And this is a little bit of code that I've written. And again, we'll make these available to you afterwards. That outlines that you don't necessarily need to know what's in the file to produce a time series. And that's because the NetCDFs from the CMEMS, the Copernicus Marine Environment Monitoring Center service, they follow a convention. And that's a convention called CF, or Climate and Forecasting. And what that means is the NetCDF contains information about itself. And by being a CF compliant NetCDF, it contains a minimum set of metadata such that we know we'll be able to do this analysis on any CF NetCDF without having to know ahead of time how it's structured internally. So what we do here, this is the same as how we had on the previous one. We're just going to import some basic libraries. So we're just going to use the NetCDF library to open the file here. And then we have matplotlib and NumPy. Those are our standard workhorse libraries that we use every day, really. Again, just setting the data files and the locations. And this is one of the data sets downloaded from the CMEM system. I downloaded it this morning. So how do we actually produce a time series of this information when we don't know how the data are structured internally? This is where we then come in to look at the attributes. So the first thing we do is we open our data set and we take out have a look at the time variable. So again, we just look at the variable dictionary and we say, well, give us the time one. Now, a dictionary in Python is just a set of key value pairs. So by asking for variables and then using this as a key, it will pass us a copy of the full NetCDF variable from within our file. As it's a NetCDF variable, it has this function on it called NCAttrs, or NetCDF attributes. And that can be useful. Again, this is telling us how we can then understand our data. So if we look at the attributes associated with our time variable, we can see we've got a few here. We've got axis, calendar, long name, standard name, units, chunk size, and coordinate axis type. These two, you can pretty much ignore. They're used by computer systems. So in certain visualization suites, such as Snap and Panoply, it will use this variable here to know what type of coordinate variable this is. So it says it's time, knows it's a coordinate. This will tell it what type of coordinate. But the ones we're interested in really are this calendar and units. Because by combining calendar and units, we can actually calculate all of the dates that are available in the file without knowing ahead of the time. So if we just print out the time variable now, you can see it produces numbers that don't necessarily mean a whole lot to you or I. But what those numbers actually are, if we output all of the metadata for the variables here, and then we go to the time dimension, ADT, time. So you can see here that the time, and it is storing the data in a Gregorian calendar, and it is storing it as days since 1st of the 1st, 1950. So, okay, these numbers now make a bit more sense. So this is 25,795 days since the 1st of the 1st, 1950. Some of you may be able to calculate that in your head very quickly. I am not one of those people. But luckily, because we have this information here and this information here, we can programmatically calculate the correct dates. So what we're going to do is we're going to take off the get a copy of the calendar attribute. So that would be Gregorian. And we're going to take a copy of the units, which would be days since 1st of the 1st, 1950. And so we're just printing those out here just to show that we've pulled off those attributes. Now what we can do is we can use a function that's part of the NetCDF library called num2date. And this is built in because technically you could store a string field in a NetCDF, but that would be madness. So the NetCDF library knows that the data are going to be stored numerically. And so this is a helper function that is provided by the NetCDF library to convert these numbers back into a date. Now, the bits of information you need to be able to do that are the units and the calendar. And because those are always provided for us, we can then just use those here. So we have the date units and the calendar. And we can use this in the num2date function to convert these numbers into useful dates. So once we run that against our time variable, we get a new array. And if we now look at that array, you can see that they're actually date time objects with the correct date in them. So instead of it just saying 25,795 days since the 1st of the 1st, 1950, we can see that that's actually the 16th of August, 2020. So now that we've got these dates, it's quite simple to make a time series object, time series graph. So we'll make a couple of different ones to showcase what can be done. So what we'll do is we take a copy, and I have not updated these from when I did a chlorophyll demo. As it says here, replace chlorophyll with the variable that you are currently working with. So I'm going to change that back actually so I don't break the rest of the code. So what we'll do is we take our NetCDF file, and again, we access our variables object. And this time we only want the sea level anomaly variable, and we just take a full copy of it. As we did before with the one-dimensional data, we'll just look at the shape of it using the shape attribute, which is made available by the NumPy library. And now you can see that these data sets are three-dimensional. What we actually have here is time, latitude, longitude. And so this is then an image that is 370 pixels by 578 pixels. And we have 32 of those images. Versus if we go back to the set level 2, when we looked at it here, it's still just a single dimension because it's the level 2 data. So we know that we've got these images here and we've got 32 of them. So what we can do for our time series is initially we could just do, if we were being, we had subset the area using the CMEMS tool to just be the area we were interested in. Maybe we want to just look at the average over the whole data set for each timestamp. So what we can do is we can just loop over using the Python built-in function called range. So you pass a number into range, and that will tell it how many times to loop. We know that the time steps is the first item in this shape, so we can just utilize that value here. So we know that there are 32 time steps, so we can just pull that again. We didn't need to know. we can take it directly from the shape object. And then each time step we go through for this first basic idea, let's just mean the whole data set. So we've subset already to the area we're interested in. And so we don't need to subset the data ourselves here. We can just take the whole data set. So to do that, and we just populate this array of means here using a function in NumPy called nanmean. And all that does is it just excludes pixels which don't have a value. That's not low values, that's pixels that actually have 0 value. Whether that pixel was an error or whether it's been flagged out for various reasons, it will get rid of it and it won't include it in the average because you wouldn't want it to. And once we've got those means, it's pretty easy to plot them because we've done all of our hard work getting our date time list. So now what we can do, this is just a little helper that I have in here because I'm running lots of plots. It just says clear figure. You wouldn't probably need this in your own, but I've been running this sheet a lot. And then what we're going to do is we're just going to use plot subplots just so we have access to the figure object. And this is just so that we can set the date format. So we know we've got these dates and we want to display them nicely. So we can then format them like this. But we've got our means and we've got our dates. And so to plot them as a really nice simple time series, you can just do plot.plot and you pass in your dates as the first array and your means as the second array. And then we have our plot. And so this is the sea level anomaly over a very large-ish area of the Northwest Shelf between the 17th of August and the 17th of September. And you can see there was just a steady rise in it. Now, I won't explain why because I'm not sure, but this is just the data that I extracted. If, however, you extracted a file from CMEMS that covered more area than you were interested in, maybe you were extracting data, say, for multiple locations, and so you downloaded a file that covered all of those locations, because that would be sensible. What you can do is you can extract a single point from your NetCDF. So again, what we can do is we just specify the latitude and longitude that we would like to extract our point for. And then using a little simple bit of maths, we can then find out which location in our latitude array and our longitude array correspond to these values. And the simple maths is basically, we take the latitude variable, which is a one-dimensional array of latitudes from the NetCDF, and we take every element in that array and subtract our desired latitude from it. We abs that so that we get rid of any negatives. And then we take the smallest value that returns. And the reason that works is quite simple. So by taking away the latitude we're looking for from the list of available latitudes, the one with the smallest difference will be the closest pixel to the one we are looking for. And so we can use that for both the lat and the long to return us the index in those arrays that will correspond to 49.2 and -9. And so you can see we run that through and we can see that it's pixel 234 for our latitude and pixel 168 for our longitude. So now we can run through the same loop that we did before, but instead of meaning the whole data set, we're just going to extract a single value from our data set. So here is our full data set. And we have each of our time steps inside this loop will be X. So the first time we come through, it will be 0, second time 1. And we've already calculated our latitude and longitude index. And so we can just pass those in here. Now, this is, I'm just going to type this in. This is just a way of selecting data in NumPy arrays. So if you have a simple Python list, it'd be like this, and you can have a value in it. And if you wanted to look at a value within there, you could just do list : 0, and this will pull in the first item in this list. Now, as NumPy arrays can be n-dimensional, what you can do is you can just split the indices you're interested in by commas. So what we're saying here is we want, for the first dimension of our array, this index. For the second dimension in our array, we want this index. And for the third dimension, we want this index. So we can extract all those values, add them into an array, and then we can plot those. Now, if we look at the average over the whole area that I selected around the sort of the northwest shelf, you can see there was a steady increase in sea level anomaly. But if I look at this individual pixel, you can see we actually have quite a changing sea level anomaly. And so that's useful at looking at individual points. And then to look at an area, so if you downloaded a file and you're interested in a section of it, but not an individual point though, a bounding box, we can just say, okay, well, we need 2 latitudes and 2 longitudes for our subsetting. We then use the same basic principle here to generate the index that's associated with these latitudes and longitudes by doing the argmin absolute method. And again, so this is then given as our indexes here that we then use to chop our file. And what we can do is, so we can pass this into our nan-mean function. And in the same way, so as I said before, the way we have in dimension, comma, dimension, comma. But for our second dimension here, we want to take data between 2 locations. So we're going to say that we want all of the data for this dimension, but for our latitude dimension, we only want data in between these indexes. So we have minimum, colon, maximum. And then we have the same for our longitude. So this will then only extract the data that we're interested in inside our bounding box and then produce a mean of it. And just as a way to show a sort of a real simple feature, if you want to add a baseline on your plot, you could just create another array and just put a fixed number in it. So this is just going to then leave a line at 0, 0 for us on our plot. And we just pass those in twice to the plot. So the first time we pass in our dates and our actual data means. The second time we pass in our dates and our trend line and our baseline. It's not a trend line, it's just a baseline. And that will then give us a plot like this. And so we can see now that by the area that we were subsetting doesn't have that similar drop in sea level anomaly. So that may mean that there's actually something there that we could maybe look at. Maybe there's something to investigate. And so then you may want to actually render one of the data sets as an image. And so that's what we come to next. Now, you may recognize some of this code from the level 2 demo, where we're going to be using matplotlib, cartopy, things like this. We are going to add in an extra one here, and I'll explain why in a second. And this is from a library called Shapely, which just allows you to define your own geometries and polygons. And that's because if you were doing a quick study of this, where you've been selecting data over a particular area and running an average and producing a time series, you may want to be able to communicate what you've done to someone. And so that's what we're doing here. We're going to, initially, we're just going to plot our base data on the map. So we're just going to take an exemplar one of our 32 data set, 32 layers, and just choose one of them. By not including a value for these dimensions, it will take all of them. So because it says, okay, the first number is our first dimension, it wants the third item. He didn't provide any indexes for the other dimensions, so we'll return all of them. Again, we're going to add some coastlines. These are just some niceties to have on your plots. And then this is where we then get to the bit where we're using this to communicate what we've done to someone, whether that's in a paper, to a supervisor, to a boss, by overlaying some simple geometries. So our first one here, we're just going to add a geometry, which is ring, which we've just specified up here. And all our ring is the corners of the bounding box that we were investigating earlier, split over our lons and our lats. And then we use a small Python function here, zip, which just pushes 2 arrays together to make one. And I believe I have an example up here. Yeah, so here we have an example where we just have an array called A with 1, 2, 3, an array called B with 4, 5, 6. And if we zip them together, we then get an array which has the first item is 1 and 4, the next item is 2 and 5, and the next is 3 and 6. So to create an array of our pairs of lat and lon, it's quite a simple way to just write one array for lons, one array for lats, and then just zip them together. And then what we do is we just plot that to our map. And so because we're just telling it to add a simple geometry which is a ring, we just have to tell it a few little things that we want. So we want it to be colored red, and we want it to be semi-transparent. And that's then what we end up with here. And so this could be really useful when you want to highlight to someone, okay, yes, I've done a time series of this data. Where? Now you can put a little square on the map to show the area you were interested in. Or if you were just doing the point extraction, whether it was for a set of in situ buoys that you have maybe, or for a cruise track, you can just use the scatter. So in the same way that we use scatter to overlay thousands of points for our level 2 data track, we just need to overlay one point. And so we just pass in the X and the Y that we're interested in. And because we're using CartoPy, we can pass those in the actual latitude and longitude. We don't actually have to convert those to pixels. It does it for us. And again, you tell it the projection so that it knows the location where to put it, and we give it a color, red, and you can see that's then just put a dot on our map here. So if we were producing a nice time series of this particular location, we could produce our time series plot, highlighting any anomalies, and then we could produce a map like this, just showcasing where we were taking our data from. Okay, so that was a little whistle-stop tour of where to get data, and I'll just run over the basics again. So for level 2, we go CODA, Copernicus Online Data Access, and we search using the criteria here, and we reduce the amount of data by drawing a polygon by selecting it from the bottom down here. For CMEMS, you go to the Copernicus Marine Service, registered, log in, and then go to the services portfolio, and then start searching for the data that you're interested in. Okay, so that wraps up this section of the actual training.
Okay,
and so
thank you,
well,
Holly.
there's one extra thing I'd just like to show, Federico,
okay,
which is this page. This is the EUMETSAT main training page.
Yeah, we can do this. Yeah, there are just a few, a couple of quick questions that
okay,
I would like to push you.
Sure
okay.
thing.
Yeah, thank you. Okay,
I'll just stop sharing my screen, I think, or.
Oh, you can keep it, and we can
Okay.
comment that. No problem.
I'll put a nice picture.
Yeah, the first one is of course on the accessibility of the Jupyter Notebook code that the participants asks.
Yeah. So specifically, these ones I've shown you today will have a link to them from the Moodle page, where these course announcements have been made, and it is the same place that the recordings and presentations will be made available.
Okay.
There is a process ongoing at EUMETSAT at the moment to make more of these notebooks publicly available through a system called GitLab, and I don't think there is a way for you to sort of sign up for information about that, but when they are made public, there will be quite a lot of promotion about them, so you will probably hear about it from many people.
Yeah, okay, great. I can add as EUMETSAT that the GitLab is already open. I will put the link in the chat. For the moment, there are no specific notebook for the ocean, but there will be other that will be used for the next training. The second question is on the availability of API interface, or whatever package to access directly this data. To embed in the software. Okay.
Yeah, so there is an API for CODA. Let me just see if I can find the information. Which basically allows you to query in the same way that we were querying through the web interface, where you selected a polygon, you selected a start and end sensing time, you chose a sensor. You can send all of those parameters via a web API, and it will basically return you a list of files that match, and it will then also give you links to download those files as well. And so there is, and as part of the notebooks that are being made available, I think one of the ones that has been approved is the Sentinel downloader. And the Sentinel downloader is a small piece of code that basically allows you to fill in a config file with the information that you need. You will need to still register for the CODA website. And then it allows you programmatically to query the CODA repository and then download data as well that matches your criteria. One of the nice things about using an API like that is it allows you to do a bit more sort of clever download. So one of the data sets, so for instance, on ocean color, less important for altimetry, cloud affects data. So what you can actually do is using the API, it will download the summary file first, check the percentage of cloud cover that's represented in that file, and only download the full large data file if it's above or below a threshold that you've set. So you can then get quite creative. And again, that code will be on the GitLab.
Okay, there is, I mean, another scientific technical question. So again, the difference between sea surface height and sea level altitude.
Anomaly. A is for anomaly.
Yeah, okay.
In fact, sea surface height shouldn't never be used. You should always say sea surface height with respect to something. So sea surface height for the altimetry people is sea surface height with respect to the reference ellipsoid. For oceanographer, most of the time it's sea surface height with respect to a geoid, and meaning that it's showing you the dynamic topography, and sea level anomalies as sea surface height with respect to a mean sea surface. Which means that with the sea level anomalies or sea surface height anomalies, what you're seeing is everything moving from one revisit to the other.
Okay,
While
thanks. Yeah. Okay, thanks. I think it's clear. I mean, from what I see, there are no additional questions. So, I mean, in any case, do not hesitate to come back to us. I mean, in writing to us, in joining additional courses. So I mean, before going on the advertisement of the new. There are questions. There are additional questions.
I can answer the MSL mean sea level accuracy.
Okay. Yes.
Globally, it's 0.6 millimeter per year for the global.
Okay.
Not locally, but global mean sea level accuracy from altimetry is estimated to 0.6 millimeter per year.
Okay. Perfect. Thank you. All the other questions, I mean, there is the access of the Jupyter Notebook. We have provided elements. There are two questions on the availability of the material, and then please go on the link that has been just put on the chat. So training.eumetsat.int/course/view PHP ID 374, and here you will have all the material that we need. I think there are no new questions, right?
Well, there are several questions on the slide, or if we
okay.
have some time, we can address them, because as you can see.
Just browse them. Okay, perfect.
Yes, I mean, this was answered.
Because I don't see them. That's
you don't see them on the screen.
Okay, no, we see a few of them, but not all of them.
Yeah. Okay.
Can you scroll down? Okay, perfect. Okay, stop. Norris moment. Thank you for the presentation. A few years ago, okay, we saw a cold blob west of Canada and a cold blob south of Greenland, where it is caused by glacier meltwater. But it's better. It's only on the Vinca.
Cold blob meaning sea surface temperature. I'm not sure.
Okay. Yeah, I think it's more about temperature rather than altitude. I mean, if you want to, we can postpone it a bit. There was another one that was just scrolled. Yeah.
There's a question about using other electromagnetic
yes,
signal.
or LiDAR or whatever. Yeah, well, LiDAR system.
There is an laser altimeter, which is called, well, two satellites, ISAT and ISAT-2. The only problem is that it's very, if a radar altimetry gives a thin thread of data, giving an even thinner thread of data, and it was mostly meant for ice. and could give information about rivers and lakes, but over the ocean it's more complicated. And contrary to the radar, it is not going through when it's cloudy, and so on and so forth. So radar altimetry is more reliable. But yes, there were 2 NASA satellites called ISAT with radar altimetry.
Okay, there is just one last scientific question. Let's say, how do you deal with waves and coastal detection?
So those are 2 different questions.
Yes, of course.
The waves, in fact, what is happening is that when the radar signal is sent to the ocean, if it's really flat ocean without any single wave, it will get back nearly at the same time. When you've got waves, it will bounce over the wave crest before bouncing over the waves troughs. So you will have a much more slopier return echo. And this is this slope that we use to compute the significant wave height. So this is at what we call the waveform level. It's the radar echoes, if you want. And there are several processing to retrieve that value. And the highest significant wave height ever measured by an altimeter is about 20 meters.
Okay.
That's a big. Coast detection, we are mostly dealing, but trying not to get a mix of land and water beneath the satellites. And when we do, it's the question is to know what we've got. So it's not more complete. It's not just different in processing, but just different in taking care of what the signal is meaning. And the detection is only a mask. We don't detect the coast. We use land mask to know where the coasts are supposed to be.
Okay, great. Again, I think for all the, let's say, technical question of availability of lectures material, please go on the Moodle page that has been provided before. Before closing, I want, I would like to ask you if you can jump into the Slido and the slido.com, and the link is EUMSC1. There is one last pool that is an evaluation. It is very useful for us to hear your feedback. We really appreciate that you provide a positive feedback on the chat, but we may need to track it and to have your feedback to make better next time. I would like to close of course thanking a lot about Oliver and Vinka for the very interesting presentations and the very nice information. We have scratched a bit at the level of complexity that we have behind the data that at the end provide key information for the environment. Advertising on the upcoming courses. So if we may put up the page of the training, maybe Oliver was doing this. There are upcoming courses. There are short courses, the additional short courses that will be every couple of weeks. So you can go on the training and enroll, and also distribute the information into your organization and colleagues. And there will be, and here you see the series. So the next one will be on radiation. So a light on heat, what radiation tells about soil and air and fire. So is a very nice travel on the capability of detecting light from satellite and what you can observe at the surface. And the other ones are listed here. And maybe Oliver, you want to make some advertisement on an online course that is open on ocean applications.
Yep. So we have, as well as this whole set of short courses that Federico's just outlined. We also have one of our full courses, which is running in a few weeks, which is using Copernicus Marine Data Stream for ocean applications. I believe applications close Friday. Is that Friday? Yeah, they close Friday. So you have 2 days to submit an application, and then basically the course is structured so that we have all of it is online. We don't have a classroom anymore due to obvious reasons, but we'll have a sort of a 3-week period of online self-taught where we will introduce you with lots of topics, lots of materials, and be available once a week or twice a week to answer some questions. And then we will have a full week of virtual classroom sessions, which will guide you through some of the more complex topics, some of the more complex data analysis, as well as it will guide you through the creation of a mini project. So when you apply for this, it will ask you for some ideas that you may have around producing a mini project utilizing the satellite data. And that's one of the things that we will then help you do as part of the actual course. And so, yeah, I highly recommend that if anything today has been interesting to you and you think, okay, I want to learn in a much more in-depth, then apply for this course, and we may see you in a few weeks.
Okay, thank you very much. I mean, really, we strongly invite you to apply to participate, especially in that phase where, I mean, most of the things will happen online. I mean, we are happy to support that. So I would like to close. I mean, thanking again Oliver and Vinka. I mean, and a virtual applause to them. And I also would like to thank my colleagues, our colleagues in EUMETSAT that are behind the support nickname. So Rosa Ulucci, who has managed the session, and Manalina Ungur for the support today. So thanks again, and I hope to see you and very soon virtually on the EUMETSAT channels. Thank you very much, and have a good afternoon.